and I'm Sarah Riesenberg. And for our senior project, we worked with a company called Really Right Stuff. Really Right Stuff was founded in 1990 with a mission to deliver superior camera support systems from the ground up. Today they ship to over 120 countries around the world and are continuing to grow each year. Their product line has expanded from a handful of custom camera body plates to an extensive line of support products, including hundreds of custom plates, pano gear, studio gear, ball heads, tripods, and fluid heads. For our project, we will be focusing on their tripod assembly. Having previously outsourced production, Really Right Stuff began in-house tripod assembly in early October. Their goal? Assemble at least 20 tripods a day in order to meet market demand. Our goal? Identify any process improvement opportunities and provide recommendations to management, with our emphasis placed on facility design and 5Ets, which is contained to their upstairs assembly floor.
The agenda for this video includes familiarizing you with the tripod, walking you through the original floor layout, going over our recommendations in regards to the tripod assembly, discussing the current layout, and the cost analysis to justify the recommendations in various layouts. Before we begin, we will review the tripod components discussed throughout this presentation. At the top of the tripod is the platform, which is where the camera is connected to the tripod. The platform is a part of the apex, which is where the three legs come together. The component that attaches the apex to the legs is called the clevis. The legs are made of carbon fiber and are connected with a locking gib. The locking gib has the outer mold, which you can see, and an internal gib ramp which lets the user unscrew the legs for extension. Finally, at the bottom of each leg is a foot.
The flowchart seen outlines the tripod assembly using the pneumatic bonding machine, which we will go into further detail on later in this video. The first step of the assembly is to prepare the fixtures and legs for gluing. The top leg requires a clevis and gib ramp, the middle a gib ramp, and the bottom a foot. Each of these fixtures are glued to the legs using the pneumatic bonding machine, cleaned by hand, and then set to dry for approximately 6 hours. The gib ramps are greased so that the locking gib twists on smoothly. The locking gib is what is used to connect the legs together. Next, the legs are individually assembled. Before the final assembly, the platform and apex subassemblies must be completed. Then the legs are manually attached to the apex and the finished product is wiped down by hand and sent downstairs to the shipping department. Now that you are familiar with the assembly process, let's review the physical layout.
This here is a Visio drawing of the original layout, and the red box indicates the physical scope set for this project. This next box encaptures all of the carts that hold inventory. The first station is where the gluing occurs. Directly behind the gluing station is the table where a majority of the sub-assemblies are completed. At the bottom right table, primarily greasing and cleaning take place. Leg assembly is typically completed between the racks of inventory, and then last but not least, final assembly takes place at the top rightmost table. Here the tripods are assembled, then opened to be wiped down before being placed on a cart to take downstairs. Additionally, the toolbox is located on the far side of the room.
The original bonding procedure was done by hand gluing, which can be seen in the pictures. This was challenging for quality standards because of the inconsistent application of glue. The excess resin that resulted from gluing by hand required extra cleaning time, which added to the variation in process times. In December, a pneumatic bonding machine was introduced to the process to replace the hand gluing step. The pneumatic bonding machine significantly reduced cleaning time because the exact amount of glue per part was applied using an automatic dispenser. This significantly increased quality by minimizing variation.
In the chart, a comparison of the bonding and cleaning time is made between hand gluing, one pneumatic machine, and two pneumatic machines. The blue indicates the hand gluing time, the red represents the cleaning time, and the purple represents the bonding time using the pneumatic machine. There is essentially no cleaning time when using the pneumatic bonding machine because the operator can clean the part as the next part is being glued. As seen, implementing one pneumatic bonding machine resulted in a reduction in total bonding and cleaning time when compared to the hand gluing technique. When a second pneumatic bonding machine was added, the total clean and bond time was reduced by more than 50% of the original hand gluing technique. Therefore, the second pneumatic bonding machine proved to be a valuable addition to the process.
The following table displays the average run times for each task within the assembly process. 19 time studies were completed for this assembly with an average of 15 observations per task. The table shows the complete assembly time per single tripod for hand gluing, one pneumatic, and two pneumatic bonding machines. The total time per tripod with hand gluing is 41.72 minutes. for one pneumatic is 34.89 minutes, and for two pneumatics is 24.99 minutes. The bond times seen in the first row were calculated using a weighted average to account for 3 feet, 6 skid ramps, and 3 clevises being glued and cleaned. Note that the dry time is not included in the total time calculation because it is a significant outlier.
While observing the process, we noticed the operators traveled a considerable amount to gather the parts from inventory and tools from the toolbox. We took additional time studies for the setup procedure, which can be seen in the graph. From these results, we decided to focus our process improvement efforts on a facility redesign in order to reduce the overall distance traveled, which in turn would affect the overall time and cost.
To give you an idea of what the setup looked like, here's a visual with the flow of the operator's paths for each setup, assuming this represents one batch of 20 tripods. Now let's look at our suggestions regarding both layout design and 5S. To arrive at our new layout, we used a relationship diagram, as seen, to indicate the importance of how close in relationship to each other different procedures should be. From this relationship diagram, we created a relationship strength diagram and arranged the tasks according to their importance that they were given. The thicker the lines, the more critical it is that they are located near each other. The first layout to be seen utilizes the relationship diagram, so the various tasks are located according to their importance. It creates a standard for the location of procedures, but does not reduce a significant amount of walking distance for setup. The second layout seen shows the product flow of assembly and therefore is a more linear process layout. It reduces a more significant amount of walking and will be discussed further in the cost analysis section of this video. The distances traveled to set up each task in the assembly can be seen in the chart. The total distance walked for setup in the original layout was 1,095 feet. The suggested process layout is 687 feet, the suggested product layout 215 feet, and the current process recently implemented is 604 feet.
Throughout the process, we conducted an organizational technique referred to as 5S. From conducting the 5S method, the following solutions are recommended. First of all, shadow boards should be implemented to ensure no tools go missing and that everything has a designated place. Really Right Stuff has begun to implement shadow boards and should continue to do so for each work and storage station. A Kamishi buy board should be implemented to clearly indicate which products need to be produced each day. The double-sided red and green magnets allow for the operators to flip the red do side of the magnet over to the green done side to indicate the task has been finished for the day. Next, defective parts were noticed to be lying around the manufacturing floor with no designated storage area. Our recommendation is to implement a defect zone with red bins labeled for each type of part and its reason for being defective. These 5S solutions will help ensure consistency and standardization within the assembly floor. Lastly, an automated counter should be added to the pneumatic bonding machine to ensure all tubes are glued before being returned to the work in process cart.
We will now take a look at the current process. Recently, Really Right Stuff rearranged their assembly line as seen in the diagram. This saved them a distance for walking setup times and reduced it to only 604 feet.
Finally, we will analyze the cost to implement each of the topics covered. This first table compares the cost of using the hand gluing technique versus 1 or 2 pneumatic bonding machines. The time was calculated using weighted averages. The number of bonds are based on the TVC33 tripod, and the number of batches produced corresponds to the average number of working days in a month, assuming 1 batch is produced per day. The labor cost, bonds per tripod, number of tripods in a batch, and batches produced per month were made variables to allow for flexibility in the analysis based on changing demand. One pneumatic bonding machine saves $186.06 per month, and 2 pneumatic bonding machines saves $2,266.32 per month compared to the original hand gluing technique. When comparing the associated costs for each layout, it can be seen in the table that the original layout had the lowest total cost when taking both time and square footage into account. However, because Really Right Stuff already owns the building, the emphasis should be placed on the time saved. Therefore, when comparing the labor cost per month, it is evident that the product layout saved the most time. It is also important to note that even though the current layout doesn't appear to have saved much time or money, it is still a work in progress and will continue to be improved. To further support the cost analysis of different layouts, a break-even analysis was conducted. The break-even analysis shows that only 4 tripods need to be sold in order to justify the original process and current layout costs of square footage used. For the product layout, 5 tripods need to be sold in order to deem this layout cost-effective. Regardless, the cost of each layout is covered by profits from within one batch. This graph shows the interception point, or the break-even point, of the total cost per layout and profit as the number of tripods sold increases.
In summary, the monthly savings of $88 for the product layout does not justify a need for implementation. Rather, the 5S recommendations should be pursued and include many benefits, such as shadow boards to avoid misplacing tools, a visual whiteboard with double-sided magnets for daily tripod assembly goals, a designated defect zone to easily identify discrepancies, and an automated counter to eliminate rework. The benefit of a more organized work area outweighs the one-time cost to implement these 5S recommendations.